Yes, hello everyone. Hope you are doing great and you can hear me. Allow me share my screen. Okay, so hope everyone can see my screen. My name is Mugabe Samuel, computer science, master's in computer science, and I'll be taking you through this paper. It was our first assignment in deep learning. So we shall be going through obtaining genetic insights from deep learning via artificial intelligence. First of all, when I looked at this, I thought we would be discussing maybe Shapley or Lime, those other methods, but this was a bit different. They introduced some other approaches. Now, we approach this using model interpretation, which includes intuitive understanding of how the approach works. And there we shall get the assumptions and limitations of whatever will be under this paper. Now, of course, as you know, deep learning is very wide. It's very wide, and sometimes people get lost inside the models, and these may not make a lot of sense to humanity, but even if the predictions are correct. Some of the keywords are DNA. We all know what DNA is, deoxyribonucleic acid. So it's a sort of pattern that makes up someone. And then the motifs, we shall be seeing this very often. The motif, the basic meaning of a motif is it's like a repetition of a pattern. And in this repetition, now in biology or genetics, these motif patterns, they signify a specific sequence. They are proteins, but they signify a specific sequence. And it is from this that some of these predictions will be made, whether our DNA is resistant, disease resistant, and so on and so forth. We shall also find TFBM, which is transcript factor binding motifs, and ISM, which is in silico mutagenesis. We shall talk about these in the subsequent slides. This approach, it was mainly encircling around sequence to activity models, where you have sequential data. Sequential data, you're looking at time series data, sequential symbols like text, or sequences of images. These come in, they come in sequentially with time. For example, time series, you get a continuous time today, then tomorrow, then like that. Now, this also is applied to these DNAs. These DNAs are like characters. It's like a long string of characters, which is also sequential data. And this is what we're going to be looking at. A number of approaches have been given. A number of approaches have been given, but of course, all these, they lead to getting lost in the models. And these deep learning models take in a lot of parameters. They take in a lot of parameters and learning for the learning and training. And then these parameters, because there are very many, it is very hard to understand which parameter makes sense out of this. A number of approaches have been suggested to reduce this, but all these have limitations. For example, the gradient-based perturbation, then also the game theory-based analysis was also suggested, but they have limitations. Another key to this inability is to systematically evaluate and interpretation strategies. It is mainly because why this challenge comes up is mainly because there is no specific data set for all these explainable AI algorithms. There's no a benchmarking data set that we can pin to and then say this is true or this is correct. This is a correct prediction, sort of like a train test. And then you have what is true, that these features are truly the ones affecting the model, or what is not true. That is the other challenge that we was identified in this paper. So moving on, we'll look at model-based interpretation, and we shall first look at the first layer convolution, whereby there are some mathematical computations that are applied to give weights and come up with a weight matrix. Then it is to this weight matrix that these motifs, depending on the number of times they appear in the sequence and at what position, that affects the size. Now, for example, as you can see, the character T in position 4, according to this position weight matrix, T appears very many times in this DNA. That is why it is having a very big, the size is very big and the bits are very big, and you can cross-check that with this. Now, this model-based interpretation, there is one of the strategies, and then another is node-based strategy. Now, for this one, they just input parameters into the nodes, and then try to observe. They keep altering the parameters that are being put in the model, and then try to observe what impact is there for removing this parameter, what impact is there for nullifying. They measure the impact for adding or removing a feature, and then it is to that where we shall see whether it is of high importance or low importance. Now, these approaches also, they suggest a sort of attention mechanism where you can visualize feature importance. Now, of course, all this, they start with regularizing the weights, so as to avoid overfitting, to avoid the overfitting problem in that. So they first regularize it and scale it from the scale of 0 to 1. Now, there is mathematical propagation of influence. And the way this was approached in the paper is they wanted to come up with strategies that are model agonistic. What do we mean by model agonistic? That the approaches are sort of above models. They don't only work on a specific model. This is useful because it helps overcome the problem of being it overcomes the problems of individual models. Now, for example, if you use a specific strategy, it has its own challenges. Another has its own challenges, but these approaches they wanted a model agonistic approach. And these were divided into two major groups: forward propagation and backward propagation. Now, for forward propagation, looking at forward propagation, the main highlight that I picked out from the paper was the in silico mutagenesis, ISM, that I told you that we will be explaining here, which is, it's sort of a computation technique that involves alternating individual nucleotides in the DNA sequence and observing the resulting change. Now, these individual nucleotides in the DNA, they keep varying them while observing and taking note of the predictions. And in this varying them, it is from this that which features, the most important features to the model are observed to explain why a model is predicting this and this according to those features. Yeah, just like you can see in the illustrations there. Now, backward propagation, on the contrary, it's not like the forward propagation, whereby you're giving it and then you're alternating. Now, backward propagation, it sort of addresses the computation problem, which the forward propagation was picking from the model. The forward propagation had some computation problems, and backward propagation is sort of trying to address that. and it sort of calculates a gradient from the model function with respect to the features that you have fed into it, then using the chain rule, and then backwardly propagate through the network. Of course, from there it comes up with a propagation map, a gradient-based an attribution map, from which the features of the model predicted depending on the feature importance. But also in there we get saturation problems. We get some saturation problems like any other model. Conclusion for this paper and future perspectives. Now this paper, uh, it sort of concentrated on sequence to activity models. That was the main approach to this paper, which is understandable because DNA data is sequential data, and so should the models. But what is most important to note here is that you have to start with a target in mind. You have to understand the biology behind and come up with a target that you want to achieve. You have to have industrial knowledge about this field before you apply these models, because sometimes when you overfeed these models with a lot of parameters, for example, you give it a lot of parameters, then maybe the data set is small. You have a small data set and you're giving it a lot of parameters. These models tend to come up with patterns and shortcuts that are not biological, non-biological patterns and shortcuts. Now, if you don't know the biology behind, this can easily skip you. But now if you know the biology behind, you can easily guide the model and you know that this and this pattern or this shortcut doesn't exist. This exists. And just like most AI papers, also this ended that with hope to maturation of the field and establish, sort of integrated tools that can help analyze this feature. Yeah, that's all I had. That's all I had for you. Yeah, thank you for listening.